In this video, we're going to find area under a curve using the fundamental theorem of calculus from section 5.4. We'll be starting with problem number 9 from the textbook. If you want to follow along, you'll be able to see the pictures there, but I'm going to actually solve these without the picture so that you can see how to do this even if the picture isn't given to you. So y equals x minus x squared. We want the area between this curve and the x-axis, y equals 0. So I'm going to set this equal to 0 and solve. X times 1 minus x equals 0, x equals 0, or 1 minus x equals 0, negative x equals negative 1, x equals positive 1. So those are my boundaries from 0 to 1. So my interval that I'm interested in here is 0 to 1. Let's talk about the fundamental theorem of calculus for a second. It says that the area under the curve between the curve and the x-axis can be given as a to b of f of x dx is equal to the antiderivative evaluated at b minus the antiderivative of f evaluated at a. We've done antiderivatives, but haven't used the word antiderivative so far. The integral gives us an antiderivative. Usually we have a whole bunch of them that work that vary by a constant of integration plus c. We're not going to worry about the constant of integration here. We just want the rule without the plus c on it, and we want to evaluate that at the limits. So let me go ahead and show you how to do this one. So we're going to take my area is equal to 0 to 1 here, and then f of x is x minus x squared dx. So using my rules for sum difference of integration, that's going to give me 0 to 1 of x dx minus 0 to 1 of x squared dx. So the new thing in this section is that we have these bounds that we have to deal with. So if I were to integrate x dx, I'd get 1/2 x squared, and I'd normally put a plus c. I'm not going to do that. I'm going to evaluate that from 0 to 1. And if I were to integrate x squared, I'd normally get 1/3 x cubed. And I would put plus c, but I'm not going to do that. I'm going to evaluate from 0 to 1. So I'm going to put in my upper limit here. This is 1/2 of 1 squared minus 1/2 of 0 squared minus 1/3 of 1 cubed minus 1/3 of 0 cubed. Okay, those parts with the zeros multipliers become 0. So this is 1/2 times 1 minus 1/3 times 1 is 1/2 minus 1/3 is 3 minus 2 over 6 is 1/6 for my area. Let's go ahead and let's look now at number 11 from the textbook. And if you look at the picture there, you're going to see that I don't have any x-intercepts there. I just have to use the picture that's given to me to get my limits there of 1 to 2. So 11 says that I want y equals 1 over x squared, and my boundaries are 1 to 2. So we'll set that up that my area is going to be 1 to 2, 1 over x squared dx is 1 to 2 x to the negative second dx. So a is going to be x to the negative 2 plus 1 over negative 2 plus 1. That all gets evaluated from 1 to 2. So that's x to the negative first over negative 1 from 1 to 2 is a negative 1 over x evaluated from 1 to 2. So my area is going to be negative 1/2. Then minus a negative is going to be a positive 1 over 1 is 1. 1 minus a half is a half. Let's look now at number 13. Again, I can't solve for the x-intercepts because this curve actually doesn't have any x-intercepts. So 13, y equals 3e to the negative x over 2. They've given me the interval of 0 to 4 that I'm interested in for my x. And so a is integral 0 to 4, 3e to the negative x over 2 dx. I'm going to go ahead and pull that 3 out. It's not very helpful. I'm going to call u negative x over 2, or negative 1/2 x. du dx is negative 1/2. du is a negative 1/2 dx. I'm going to multiply by a negative 1/2 on the inside, multiply by a negative 2 on the outside to balance it out. That gives me a is equal to 3 times a negative 2 is a negative 6. And then I have integral of e to the u du. If I'm going to change the variables on the inside, this part called the integrand, to be u, I need to change my boundaries to u. So I'm going to use this formula for what u is equal to. U is equal to negative 1/2 times x. So negative 1/2 times 0 is 0. Negative 1/2 times 4 will give me a negative 2. I can leave it just like that. I shouldn't, since negative 2 is smaller. So I'm going to show you a property here that says that if I have the integral of a to b f of x dx, and I want to switch the limits of integration, I can do that by putting a negative out front. And so let's go ahead and do that. The opposite of a negative 6 is a positive 6. We'll make this go from negative 2 to 0, e to the u du will be 6e to the u, evaluated from negative 2 to 0. So that's 6 times e to the 0 minus e to the negative second will be 6 times 1 minus 1 over e to the second. And let's see, that is equal to 6 times e to the second minus 1 over e to the second. Exactly. Right. Let's wrap up now with number 15. Yes, 15 says y is equal to x squared plus 4 over x. And again, I'm given an interval here of 1 to 4 with the picture that they gave me. So let's go ahead and set that up. My area is going to be 1 to 4 of x squared plus 4 over x dx. We'll split that into 1 to 4 x squared over x dx plus 1 to 4 over x dx. X goes into x squared x times. X can't be 0. 0 is not in the interval, so I'm in good shape. 1 to 4 x dx plus 0 is not in this interval either, so we're in good shape. 1 to 4 of 1 over x dx. So this is 1/2 x squared, evaluated from 1 to 4, plus 4 ln of the absolute value of x, evaluated from 1 to 4, is 1/2 of 4 squared minus 1 squared, plus 4 ln of 4 minus ln of 1. ln of 1 is 0. This is 1/2 of 16 minus 1 plus 4 ln of 2 squared. So that is, let's see, 15 over 2 plus 2 times 4 is 8 ln of 2. And that's my exact answer. I can get a decimal approximation for that if I would like to. So we'll come back next time and talk about evaluating definite integrals that do not necessarily represent area. Remember, the area is a positive value. I can't get any negative answers that are meaningful for area problems, but I can evaluate definite integrals and get any real number, and sometimes that negative number is going to be meaningful in certain contexts. So while I can use definite integrals to find area under a curve, that's not the only time that I get to use definite integrals. I can just solve a definite integral without any context of a word problem for what it represents. It may represent nothing other than the value itself, or it may represent something else in business or science or something like that, and that negative value may have some meaning. So, all right, we'll come back and talk more about definite integrals next time. See you for the next video.